The last video explained why it's important to take our transfer function coefficients and convert those into poles and zeros by way of finding the roots of both the numerator and the denominator. Now, there's a pretty famous way of finding the roots of a three-element vector of polynomial coefficients, and that is the quadratic equation. I have it written up here, and there's a really important feature of the quadratic equation, and that's when the quantity 4ac is greater than the quantity b squared. The output of the quadratic equation will be complex. And of course, that's because the argument to the square root part of this function will be negative in that case. And when the argument to a square root function is negative, its output is imaginary. Now, you can see here that I've allotted outlets considering the fact that there might be two roots, and each root might have both a real part and an imaginary part. We're going to exploit a particular behavior of the square root block in PureData, and that's that when it is passed a negative input, it just yields 0. So for all negative inputs, the square root block gives 0. And that's actually going to be really handy for us. Of course, it's common to state the quadratic equation in terms of a, b, and c, and so those are my inlets. Now, the most important part of this function, as we were just talking about, is that argument to the square root function. That's kind of what gets done first in our tree here. We have b times itself, and we have c times 4 and times a, and then we have b squared minus 4ac. Now, again, if b squared is greater than 4ac, what will be yielded at the output of this minus sign is a positive number. It'll get passed to the square root, and essentially everything will behave as we expect, and we'll get two real valued outputs. And just like I said, in that case where the output from this minus block is positive, I'm just going to take that and multiply it by -1. And so now I'm passing something negative to this square root block over here. And so this part of the tree that feeds the imaginary part will then all just become 0 because the output from this point on, this square root block, is going to be 0. And in that case, we have no imaginary output. And so conversely, when the output from our minus block over here is negative, that means we want to have an imaginary component to the output. So when it's negative, this square root on the left side is going to yield a 0. And what will happen is that the real components will then only essentially be made up of -b divided by 2a, because we'll be adding a 0 here and we'll be subtracting a 0 over here. Again, the use of this -1 is going to flip the sign of the argument to square root. So we're on the left. In this case, the argument was negative and it yielded a 0. Now the argument is supposed to be negative, but I'm changing the sign, and so the argument becomes positive, and now I've yielded something from the output of my square root object, and I can do my division through by 2a. And so that will yield my two imaginary components. Of course, I'm not explicitly dealing in imaginary numbers. I'm not explicitly dealing with complex values here in PureData. PureData doesn't work explicitly with complex numbers. Now again, we know the inputs to our complex pole and complex zero objects are meant to be complex, as they are so named, and the inlets are broken up to separate the real part and the imaginary part. So this is going to feed those blocks quite nicely. So we have the real part and the imaginary parts already separated. And we have a pair of roots here, which means that when we invoke this roots patch, we're going to probably be using it with a pair of either complex poles or complex zeros. And so we'll connect the real outlet of the first root and the imaginary outlet of the first root to 1, of those filter blocks and then the real outlet of the second root and the imaginary outlet of the second root to a second filter block. And we'll discuss the kind of overall implementation in our next video by use of this roots function and by use of the low pass coefficients function that we already discussed.